Hello, in this video we're going to learn the derivative formula for quadratic functions, and this is the second and the last derivative formula that we need to learn for this semester. So far it's not that difficult, right? The quadratic functions derivative formula is not difficult at all, just like what we did just in the first video. Let's consider a quadratic function. For example, this is the total cost of a firm. TC, total cost. Q, that's the output level of the firm. TCQ means the total cost when the firm is producing Q units. How much is the total cost? Well, somebody tells us that it's equal to 2.5 times Q squared plus 3Q plus 10. If you still remember what a quadratic function's graph looks like, you will realize that as Q increases, it's going to be steeper and steeper. So in other words, as Q increases, the cost will increase faster and faster. That's usually what we see in the real world about the total cost. Okay, we're not going to discuss the cost function in detail here. Let's focus on the derivative here. In other words, when Q increases by 1 unit, how much will the total cost increase? That's a very realistic question, right? A very relevant question. When we increase the output, how much will the total cost increase? Yeah, that's a question we need to answer. Well, that's also a derivative question, because we're actually asking when Q increases by 1 unit, how much would the TC increase by? That's what we want to know, right? Now, this is equal to, well, equal to that, equal to the first line. What is that? Well, we're just plugging in the total cost function. We're not doing anything magical here. TC, well, actually I should write TCQ here, and it's not a big mistake, but I should put TCQ here. TCQ that is equal to 2.5 Q squared plus 3Q plus 10. So let's plug it in just to make it easier. Okay, so that's the derivative. Now we plugged in the total cost function. Okay, here's the formula part. Your math professor will teach you this formula, but in more detail, in a more rigorous way. But here, we'll just learn how to use it. Whenever we see a quadratic function, and if we want to calculate its derivative, we first write down a number 2. Some students may ask, where does the number come from? Well, if you really want to know where it comes from, you can think that it comes from here, from the exponent. Okay. Here. Why? Well, I really don't want to explain why. Your math professor will explain why. And at this point, just believe me, we need to write a number 2 here. And then we get the coefficient of the quadratic term. And we put it here. 2 times this coefficient. Finally, we need to put Q here. Sometimes this quadratic term may be here. It may be here. But as long as it's the quadratic term, we need to do this. Write down 2, write down the number 2, get the coefficient of this number. If it's a negative number, then get that negative number, put it here, put a parenthesis around it. And then put this input variable here. That's the first part. Second, let's look at the linear part. We need to get the coefficient of the linear part and put it here as the second part of the derivative. Okay. So that's the derivative of a quadratic function. Sounds like a new one, but actually it's not that new. It's just a new some new rules. We always write down number 2. We get the coefficient of the quadratic term and put it here, and then now we put the input variable here. Then we put the coefficient of the linear term here. That's the derivative of a quadratic function. Again, when you are doing your homework, don't draw these arrows. Please don't do that. It's a very informative way of writing your homework. Okay. That's our intermediate answer. Of course, you can simplify it to 5q plus 3. That's fine. Maybe you should do that. And in this example, we know that the firm is currently producing 10 units of output, so we can plug in q and see what the derivative is equal to. Okay, when q is equal to 10, let's plug it in. The answer is 53. So now we want to know what this number means. In this class, many times I'm gonna ask you to explain what the answer means. We don't just want to do calculations. That's what we do in a math class. In this class, we want to know what we are doing. What does the number 53 means? It means that when Q increases by 1 unit, TC will increase by 53 units when we are producing 10 units. It's very important to emphasize that part. We're producing 10 units. When we're producing 10 units, let's write it in a more formal way. The answer means that at the current output level, or in other words, at the current value of Q, or you can say when Q is equal to 10. Anyway, you need to emphasize this part. You need to specify the value. Okay. So whenever you're talking about quadratic function, that's how you write it. Remember, for the linear function, we say for any value of q, but here it's different. At the current value of q, when q increases by 1 unit, TC increases by 53 units. Or in other words, the change in TC is 53 times the change in q. That's another way to explain the answer. Some students will calculate this and they'll find that it's not equal to 53. Yeah. In the future, your math professor will explain the discrepancy between these two approaches. Okay, here are 2 remarks. Let's see. Yes, the derivative of a quadratic function is something like that. Okay, it has a q in it, right? So the derivative changes when q changes. When we have a different q, we have a different derivative value. That's why we want to emphasize this part at the current value of q. It's the first thing we need to remember. Actually, I just said 2 things at the same time. Yeah, these 2 remarks are very important. You need to look at them and remember them. Okay, so this is the derivative formula. Again, remember that according to our definition, the change of q should be small, but when we're explaining it, we're just saying that it increases by 1 unit because 1 is easy, is a simple number. Now let's try a different approach, the numerical approach, and see if we get a similar answer. Let's increase q by a small quantity and see how much q increases, and then I calculate the ratio between them. Okay, so this time we don't get to choose q because the question says that q is equal to 10. So we're going to use 10. When q is equal to 10, the total cost is equal to 290. Okay, so currently the total cost is 290. Let's assume the output level will increase by 0.01, which is a very small number. If you increase by a large number, it's going to create a lot of discrepancy between the answer here and the answer here. Here we're going to choose a small number, small increase. When delta q is equal to 0.01, the new total cost would be well, this is the new output level, right? 10 plus 0.01, we plug it into the cost function, and that's the new total cost. Why does the cost increase? Because we're producing more goods, right? How much does the total cost increase by? This much. Now let's calculate the ratio between these 2 values. The change in the total cost divided by the change in the output level. Remember, we assumed this change, and that's going to be the result of that change. The change in total cost divided by the change in the output level is equal to 53.025. 5. Okay, let's compare the answer. The new answer is close to the one we got with the derivative formula. That's true, right? Here, with the derivative formula, we got 53, but with the numerical approach, we got 53.025. That's fine, because remember our definition for derivative says that the changes should be small. Actually, your math professor will say it's infinitely small, but here 0.01 it's small, but then not that small, right? Not infinitely small. So that's why these two answers are not exactly the same. Some people will ask me, well, last time when we were doing linear functions, these two answers are exactly the same. Yes, linear functions, they are special, but for any other functions, these two approaches, the formula approach and the numerical approach, they will produce different answers. So this is all we want to know about the quadratic function. Now the derivative of the quadratic function. Now let's look at the sample question, and you should copy these parts in italics when you're doing your homework. Just change the numbers, change the symbols. That's all you need to do. Okay? It sounds kind of boring, but we need practice, right? We first practice, and then maybe we can do something creative. Now let's look at this question. Consider the total cost 3q squared plus 5q plus 100. Q is the output level, and we know that q is equal to 12 currently. First, we want to find the derivative of the function. Okay, the derivative of a function. Now, first of all, remember, you need to write down this sentence. You want to greet your readers with words, sentences. Everything in your solution must be in a sentence. Actually, you can see here we have punctuations here, right? Period, period, period. We don't have any fragments here. The derivative of the function is equal to, that's the definition. Then now we plug in TCQ. That's 3q squared plus 5q plus 100. Now we're going to apply the derivative formula. Whenever we see something like that, first we write down a number 2. No reason, just write down 2. And then we get the coefficient of the quadratic term. So that's 3, 2 times 3, and then now we put q here. No reason, that's just what the formula tells us what we need to do. And then we need to do something about the linear form and linear term. We get its coefficient and put it here. What we did just now is simply what the derivative formula tells us what we need to do when we see a quadratic function. Okay, so that's the derivative. We have a q in it, and we know that current q is 12, so let's plug it in. The answer is 77. What does the answer mean? I mean, the question asks us to explain what it means. Well, this is what it means. It means that at the current output level, in other words, when q is equal to 12, at this point, when q increases by 1 unit, TCQ increases by 77. Okay, let's highlight this number so you know where we got this number here. Again, this part is pretty much the boilerplate part. You always copy this part, and the only thing changes is this number. Actually, the entire sentence is always the same. You only need to change the symbols and this number. Okay? You may think this is very simple, but well, let's first remember what we should say, and then let's try to be creative. First, let's learn the correct way to say it, at least one correct way to say it, and then maybe we can use our own words to say it. Okay, that's the first part. Now what we want to use the numerical approach to verify the answer. Well, we don't get to choose q. Q is equal to 12. Let's calculate the total cost. Then let's increase the Q by a little bit, 0.1. Maybe you can choose 0.2. Maybe you can choose 0.01, 0.001. It's fine. Anyway, the new total cost will be 599.73. So given these results, we know well, here the change in TCQ is equal to the new total cost minus the old total cost. The change in Q is 12.1 minus 12 because we suppose the output level increases by 0.1. We get that 7.73 over 0.1. Yeah. The numerical approach gives us an answer of 77.3. Okay, the numerical approach gives us an answer that is close to the formula approach. Close to the answer that we got with the formula approach. So it's right. It's almost it's close. I mean the again, the definition says that the change of the input variable should be very small. Your math professor will make it infinitely small. But here, we are using a change of 0.1. We think that's small, but not small enough. So we're going to see some difference between these two numbers. Now, when Q takes different values, would the derivative of the total total cost function be different? Well, yes, because its derivative is equal to that, and we have a Q in it, right? If we plug in a different Q in it, we're gonna have a different derivative value, right? So that's our answer. It varies with Q, so the derivative of the function would not be the same when Q takes different values. That's all. When you are working on your homework, please pay attention to the format of your solution. Flash left all your sentences, center all the equations, copy the punctuations. Before each equation, we need some words. We pay a lot of attention to the format in this class. What else do I want to say? Keep your work tidy, clean. Okay, that's all I want to say. If you have any questions, please let me know.